For a motivating example, consider a logging subsystem for some application. Events, errors, warnings, and other messages must be logged to a file, perhaps for auditing or debugging. Well, there can be only one instance controlling the log, one place to talk to the file system, that is, and that means we need to control access. This is a classic use case for the singleton pattern. Let's look at one possible implementation. For this demo, I'll be using Visual Studio Code, a relative newcomer to the crowded IDE space. Code is a free, lightweight IDE from Microsoft and runs on Windows, Linux, and OS X. This is a typical code session. I have a simple Python program in the editor that just prints the version. Open files are arranged in tabs, which you can see above the Edit window, and navigation between them is easy. On the left you can see 5 icons which open different window panes. Topmost is Explorer, where you can see your open files and all files in the current directory. In VS Code, projects and directories are equivalent. Under Explorer is an icon for Search Replace, which functions pretty much as you would expect. The third icon shows Git access, which we won't be using in this demo. Under Git is an icon for debugging, which we'll use to run our programs. Note the 4 different subviews for variables, variables to watch, the call stack, and breakpoints. The last icon is for access to extensions. There is a large and growing extension library. Python itself is an extension, as are other programming languages. So let's run this program. If I click the debug icon, the view in the left window changes. Above it you can see a green arrow, which I can use to run my program. Let's do that. Note that the debugger stops just before starting execution. This is actually a configurable property found in the file launch.json, which looks like this. In fact, all configuration in this IDE is done using JSON files. Here we can see the attribute stop-on-entry is set to true, which is why the debugging session stopped where it did. This can be changed to false if you prefer. Back in my sample program, I'll click the green arrow. The program runs, but where's my output? We can see that in the debug console. You can see that I'm running Python 3.52 in this session. Now, perhaps you don't like the dark screen. No problem. We can change that. If we go File, Preferences, Color Theme, we can change it to the light theme. And there we have a theme with a white background instead. But as for me, I prefer the dark background, and that's what we'll be using. Okay, now that we're a little familiar with the environment, let's look at the classic singleton pattern. In the classic pattern, singleton objects are not instantiated like other objects. The class definition provides a static instance method to use to access the one instance. This method does a little reflection and looks to see if the variable instance is already defined in the class dictionary. If not, it instantiates a new one and saves that reference in the instance variable, which also causes it to be added to the class dictionary for the next time around. To prove that the singleton does what it's supposed to do, we call the instance method twice for 2 different variables and test their equality. In Python, the is operator checks that the 2 objects are actually the same. Scrolling down, you can see that I've also set the S1 variable ans to the value 42, then asserted that it's the same in S2. If singleton works as advertised, then all the asserts should pass. Let's run the program to see if they do. Down in the debug console, you can see the assertions passed message, so it works. Here's the singleton pattern implemented for the logger class we want. It's the same as the singleton class we just looked at, except for the addition of the methods openLog, writeLog, and closeLog, which do the actual work of writing to the log. I've also included logic to test this. First, get the one instance, then open the log, write a record to it with a timestamp, and close the log. Finally, I have a few lines to read the log and print it out to see if it actually got written. Running this, you can see that it works as expected. Now that we have a working singleton logger, let's pause and take a look at some of the downsides. What's wrong with singletons anyway? Well, for one thing, singletons violate the single responsibility principle. They do two things. They look after their own instantiation, then hold and process that state. The logger class, for example, instantiates itself using the instance method and also keeps the state of the logger file object and performs open, write, and close operations on it. They also have non-standard class access. To get an instance, you have to note that the class is a singleton and use the instance method. Well, that's fine if you write the code and maintain it forever, but just how likely is that? They're also harder to test. Since singletons are tightly coupled with the objects that use them, it is hard to swap them out with fakes or mocks for unit testing. Singletons carry global state, like that log file reference in the classic logger class. In a sense, that's no better than globals generally, which have well-known testing and maintenance problems. Also, because the class carries state, it is harder to subclass or use for other purposes. There are a number of good write-ups of singleton problems which are worth looking at. Here are just two of them. Well, because of all of these things, singletons are sometimes called an anti-pattern.